Department of Physics and Astronomy, and also the Physics and Astronomy Alumni Board, which I will sometimes call the PAAB. Was everyone on this call even aware of the PAAB? We have a rather fluid purpose, but the board has decided that building a community of alums, faculty, both active and retired, undergraduate and graduate students is an important focus of the board. We look forward to more events such as these going forward. Before we get underway with the presentations today, I'd like to take a moment to thank former Department Chairman Hugh Feldman and former faculty liaison Alice Bean for their helpfulness to the PAAB, keeping us engaged with a sense of purpose. The PAAB looks forward to working with current department head Chris Fisher and current faculty liaison Daniel Takaki. Sorry, Daniel. And we're looking forward to the year ahead, and we'll see. Let's see here. I want to show you the current participants in the PAAB. We have these 9 members currently. These are active members. There are a few other persons on the list, but they are not participating actively at this time. We look forward to whatever they contribute as their time becomes more available. At the end of the meeting, I'm going to present a slide that has contact information for Chris and Daniel and myself. So please reach out to one or more of us if there's an interest in serving on the PAAB. And finally, a note about logistics. We do have a fairly full agenda today. If anyone has questions, please type them in the Zoom chat or send them by email, ideally by the end of the week. And we'll take care that all questions are answered. We'll post the response to questions along with the recording of the Zoom event. And with that, let me introduce Chris Fisher. Chris?
Hi, everyone. Thank you, Colleen. Thanks to everyone who helped organize this meeting today. It's great to see everybody. And I don't want to take up too much time because I know there's a busy agenda. But I just want to talk about a few things that are going on in the department and they're coming up in the department. So we just talked about the eclipse a little bit. There is going to be an eclipse event on the KU campus if anyone wants to participate in that. It's going to be at the practice field, although it's a concrete pad for the marching band. That's just a little bit west of the Lead Center. So parking is probably going to be in the Lead Center and then kind of walk across the street there to that. I unfortunately am not going to be in Lawrence. I'm going to be in Dallas watching the eclipse. But I know that several of the astronomers have events planned for that. I want to let you all know that we are currently actively involved in a search for the Stranahan Assistant Professor of Experimental Physics. So I'm currently going through negotiations with the dean about some possible partner accommodations. We'll see how this all plays out, but I'm hoping that we can converge on a hire sometime in the next few weeks. When that happens, of course, we'll let everybody know. There has been a huge uptick in overall enrollment at the university. You may or may not be aware of this. So last fall was the largest class in I forget how many years. And this fall looks like it'll be even bigger. So most of this increase in enrollment is directed toward the professional schools. So School of Business, School of Engineering especially, but there have been increases in the college. And we in the department have seen probably on the order of a 5 to 10% increase in undergraduate enrollment, which is great. A lot of that enrollment is directed toward astronomy, and that kind of mirrors some trends that we see nationally. So those are all very positive signs. It's been a learning curve for me being the new department chair, but I want to thank everyone, Daniel, Hume, Michael, everyone who's on the call here, and everyone else in the department for their patience and their kindness as I've made mistakes and learned from them moving on. And I hope that as many people as possible can come to the department banquet on May 3rd to kind of celebrate the end of a very busy but very successful year for all of us. And I believe that's all that I want to say. So I'm happy to turn it over to somebody else. I think you're mic'd, Colleen. You're muted, I mean.
There you go. We will be having an alum talk today by Joe Shields in place of Mara Payne. Joe, thank you for being available at last minute notice. Appreciate it very much. Joe?
Sure, happy to join you today. I spoke some last year, so I'll try to show you something new. I do have sort of an exciting new result that might be of interest here. So let me share my slides. Okay, can you see that?
Yes.
Okay, so I'm the director of the Large Binocular Telescope Observatory. I've been in that role for going on 2 years now. And the LBT is, as the name suggests, has 2 large mirrors, 8.4 meters in diameter, which gives it the equivalent in terms of light collecting power to a single 11.8 meter diameter mirror. And the other aspect of what makes a telescope powerful is its resolving capability. And in this case, it's the edge-to-edge baseline of 22.8 meters, which is pretty spectacular if the lights combine coherently. The location is on Mount Graham, Arizona, one of the highest, the second highest observatory site for a research observatory in North America. So that's in southeast Arizona. It has relatively good site conditions. The high altitude is helpful if you're doing mid-infrared observations that would otherwise be impeded by water vapor. So it's a pretty good site, but of course we're still limited with ground-based observations by what astronomers refer to as seeing. That's the distortion of incoming wavefronts from astronomical sources due to atmospheric turbulence, which then causes your nice point source to be blurred out. So what would otherwise be a diffraction limited image proportion where the resolution is set by a ratio of wavelength divided by aperture diameter becomes set by this atmospheric turbulence. So in the last 2 decades or so, there's been a very interesting application of technology that allows us to actually overcome the atmospheric distortion known as adaptive optics, where you monitor the distortion of a point source with wavefront sensors, and you correspondingly use a deformable mirror that reverses the distortion to the incoming wavefront. So the Large Binocular Telescope has been in the lead in some of the technology for this type of application with adaptive secondary mirrors, where your deformable mirror is, as indicated in the arrow here, is light on the second reflection. Light comes in and reflects off the primary mirror. Use the large mirrors down there and come up to the secondary mirror, which then passes it on to a focal station somewhere. The technology here is pretty amazing. The deformable mirror is made out of glass. It's a mirror about 1 meter in diameter and 1.6 millimeters thick. So it's pretty scary. Handling those, they're very fragile, but it has to be that thin in order to be deformable. And it's driven at up to about 1.7 kilohertz with 672 actuators in order to give you the modified surface to reverse this atmospheric distortion. Okay, so those are working and producing good data now. And those are now coupled with some new instruments that have just been arriving at the Large Binocular Telescope in the last couple of years. And these, there's sort of a cumbersome name here, System for Chronography with High Order Adaptive Optics from R to K band, otherwise known as SHARCs. And that's what we call them because we usually can't remember this long name. There's the SHARCs, there's 2 channels, one on each side, one for near infrared bandpass and one for visible bandpass. And the whole motivation here is high contrast, high resolution imaging, where the science driver is primarily for the study of exoplanets, so planets around other stars, where you need to detect a faint thing next to a bright thing separated by very small angular separation. So these 2 instruments arrived within the past 2 years and have been undergoing commissioning and are performing very well, and first for science results are starting to come out, and I wanted to show one of those today. So this is something I think people here will be familiar with and can relate to, which is the moons of Jupiter, the Galilean moons, the bright moons, and the innermost moon is Io, which was discovered in the late 70s with the Voyager flyby to have remarkable volcanic activity induced by tidal heating by Jupiter and interactions with the other planets. And it looks like a pizza with these volcanoes going off and so forth. So as a demonstration of the SHARC-VIS instrument, this was pointed at Io, and you can see the result here. And this shows an interesting comparison between what you see from the ground and from space, except the comparison may not be what you expect, because the space-based observation is on the left from Hubble and the ground-based observation is on the right. And what you're seeing here is the improved resolution if you're in a diffraction limited case, where you have an 8.4 meter mirror on the right and a 2.4 meter mirror on the left. So beyond just being a pretty spectacular image, the science here is studying you can actually see changes in the surface as a result of volcanic activity. For example, you see where the orange circular structure around one of the major volcanoes there has been modified. It's rather incomplete at about the 2 o'clock region, which is understood as being due to more recent activity by an adjacent volcanic structure. And you can see the surface of this object being repaved basically in real time. So that's just an initial result. And I think there's going to be a lot more exciting stuff coming in the future. So that concludes my comments.
Joe, thank you very much. I'm curious, and I apologize for the nature of the question, but on the order of how much money did that telescope cost? It's like a very amazing system.
Yeah, the all-in cost telescope plus instrumentation accumulated over the years is approaching 200 million.
But the images are awesome.
Yeah.
Do we have other questions for Joe? And Joe, thank you again for presenting today.
Sure.
There must be a mechanical limit to the size that you can build adaptive telescopes on the ground.
Presumably, yes, although the next generation of what's referred to as extremely large telescopes is emerging, is under development now. And so there are 3 of those. There's a European large telescope with an aperture diameter of about 40 meters. There are 2 US telescopes in development. One is the Giant Magellan Telescope Observatory, which has a technology heritage directly associated with LBT, in that it uses, instead of 2 8.4 meter mirrors, it uses 7. That has a site in Chile, and the mirrors have been cast and they're moving along on that, although they still don't have all their funding. The third is a sort of, the heritage comes from the Keck Observatory in Hawaii, built by Caltech and University of California. They proposed to build a 30-meter telescope. That has some difficulties, and they want to build it in Hawaii, and there's obstacles to where they want to install it on Mauna Kea, and they also do not have funding. There's a very current topic in the New York Times and Science Magazine and elsewhere where there's debate as to whether the National Science Foundation should even attempt to support 2 of these telescopes, or just go forward with funding 1.
Thank you.
All right, very good. Well, thank you again. And with that, we'll hear from Alice Bean. Alice, thank you for being with us today and presenting.
Hi, thanks. And thanks everyone for joining. I'm gonna attempt to share my PowerPoint here. Okay, so hopefully you guys can see that.
Yes.
Okay, so I'm faculty, as most of you guys know, and I'm an experimental particle physicist. And what I'm gonna talk about today is a little bit about particle physics, but a lot about what I do, which is to build tracking detectors like the one on the bottom of the screen. And so these particle, as we are in a collider, we can track all the charged particles coming out, and then we can reconstruct an image like the one on top that shows all these particles emerging. But we have to get new technology to go forward now, and that's what I'm going to talk about, the stuff on the right. So I'm a part of the CMS collaboration, which has about 3,000 physicists, and we operate this detector over here in actually France, but it's near Geneva, Switzerland, and it's in the Large Hadron Collider. And KU, we've been on this experiment since about 2003. And so the detector is near and dear to us, and it's this huge thing. And here's like a person in there. And the tracking detectors that KU has worked on, and I've worked on for several years, are all at the center of the collision, trying to figure out where things are happening. So most of you know we discovered the Higgs a while ago in 2012. So we're still studying the Higgs. There's a lot to learn. And what our group at KU has been working on lately for an analysis, the particle physicists, is we've been searching for new physics beyond the standard model. And in particular, even though I hated supersymmetry is what we've been looking for, because Chris Rogan and Graham and I, so it's a really cool group where we've been searching for the supersymmetric particles in the data. But aside from doing data analysis, we actually have to take a lot of data, and CERN Collider, the plans are to keep the CMS detector and everything to take data till 2040. So what we've been working on at University of Kansas, the part I've been working on with our postdoc grad students and undergrads, is helping to build a new tracking detector for the high luminosity LHC. And we've been building it for a while, and we hope to install it hopefully in a few years from now, and it'll start taking data in 2029. So if you look, so we take a snapshot of what happens when the beams are colliding. And really what happens is there's more than one collision. And so right now, this is an example of our snapshot of a collision. There's actually 50 collisions happening here. And we have to disentangle all of these collisions. And that's a real reason why the tracking detector is used in our experiment. Well, for the HLLXC, the one that we're building now, there's going to be up to 200 collisions. And as you can see, this is going to be really nasty. So we have to really upgrade the tracker to make that work. So that's what we've been involved in for several years now, trying to make that new detector. So I'm going to focus not so much on what that detector is, but how we get the data from the detector. So our detector is made of silicon, and it has the present detector, which we're using, has 124 million pixels, and we're taking pictures every 25 nanoseconds. And so what we do is, of those 124 million pixels, we look and see if there's a signal above a threshold. If there is, then we digitize it. And by knowing what the pixel location is, we can send that off of the detector. So on the detector, we have all of this information. And then we ship off the pixel location and the amount of charge. And then we have a whole bunch of processing to get all those tracks like in those pretty pictures. So right now you can think of a lot of our detectors having the brain off of the detector. The electronics is pretty smart and does a whole bunch of stuff, but we have to do more. So think about what happens. So we have collisions happening 40 million times a second, and the data need to be stored offline. So if you compare the CMS detector, it's putting out about 3,000 gigabits per second. And your iPhone is putting out about 0.7 gigabits per second. That's 60 pictures per second with 12 megapixels. So the CMS to your typical iPhone is about a factor of 4,000. So the problem is how do you get 4,000 pictures per second out of your iPhone continuously? Okay, so that's what we've been doing for a while now, and it's going to get worse. So if we look at our CMS detector right here, on the left, here's a big picture, and then you can see the tracking detector that's on the right being shoved into the CMS detector, and that's like 13 years ago. And then the innermost tracker goes in the hole, which you see on the right, which is closest to the detector. And we have a new one that we put in 2016. And here you can see all these silicon detectors. This is like 1/4 of the central part. And this is 3 centimeters away from the beam line. And all these silicon detectors then all have to send all their information off of the detector. So what we're doing for this upgrade detector is we're actually building all of these twisted pair cables. And we have really incredible technician at KU, Bill Burley, and he is actually having to solder all those cables personally because you can't find a contractor to actually do this kind of work. And it can't be done in Europe because in order to strip these wires, it uses this molten salt that's not allowed in Europe. So this is causing a lot of issues. You think of the cables as the stupid part of the detectors, but they're actually highly technical because we're sending the signals at 1.28 gigabits per second. So the detector we're building is a 2 billion billion as in B, pixel detector. And so we're having to get all that information off of the detector. Well, this is a non-starter for the future. So we'll be able to make it work now, but for the future, if you're going to build any detectors, you can't do this. So with some others at Fermilab, Oak Ridge, and other places, there's a detector R&D project called the Smart Pixel Project. And the idea is to put the brains on the detector. And so you make a custom integrated chip that it can actually read out all of this stuff. And it has neural networks on it, and it only ships out the information that you want. So you can reduce the data at the source. And so you're still going to be sending a whole bunch of information off, but you've already processed a whole bunch of information. So now you have the brain partially on your detector itself. So for the next detectors, they're going to be even smaller. And so you need to figure out how to get this information off the detector. So the Smart Pixel project had 2 parts to it. One was a regular neural network, but the other part is the part that I've been working on, and that's the neuromorphic computing part. Last year, Ryan Gao spoke at this event, and he was talking about work that Judy Wu's group is doing, where they're actually making these things called memristors, a new way of making computer memory that's actually really impressive. And for all of you guys who think quantum computing is where it's at, you are wrong. It is neuromorphic computing. And this is happening now, and it's in dynamic vision sensors. People can find all kinds of things that make it really cool. Well, what I'm interested in is more how the algorithmic side is working. And so what is neuromorphic computing? Well, your brain uses about 20 watts of power, and your computer uses lots of watts. So there's at least a couple of differences. So in your brain, you'll have a neuron, it'll fire when it receives a signal. And if it goes over a threshold, then it'll send that signal. In your computer, so the neuron is both a memory unit and a processing unit. In your computer, you have those separated, so your processing unit is not co-located with the memory. And so you have to move all that information around. And then the other thing that your computer has that makes it, these von Neumann computing things, makes it bad, is that everything has to be clocked and every single thing has to give information on this in this digital form. Whereas the neurons can be asynchronous. So using all of this stuff, the workhorse of this is now called a spiking neural network. And in the spiking neural network, it's temporal information that's coming, like if you look on this left plot, like in time, this middle guy will come and he'll hit this neuron, and then the neuron has a synapse and it'll hit some more stuff. And so the spiking neural network, you excite the information using the temporal information. Now, part of the issue is that if you look at how a regular neural network works, it shows the whole picture to you at once, and then it then goes in some sequential state. The spiking neural network works on this temporal thing, and you really can't convert one to another very easily. They're completely different beasts. But the spiking neural network for this smart pixel application, a group actually made a chip with a regular neural network, and then with work with the Oak Ridge group, they have made a spiking neural network, and they've shown that you can get the same signal efficiency, the same rejection, but you can use half the parameters. So this is a very energy efficient thing. I've seen at Oak Ridge now a bunch of defense drones. Everyone's starting to use this technology because it's much more energy efficient. So that was really fun. And so now we've figured out how to try and use this to help read out detectors that will have both space and time information. So the ones I was showing you before just had really precise space information, but there's new detectors that have space and time. And so I'm in a collaboration with Oak Ridge, where we're actually trying to make a neutron beam monitor where you can read out all of this information and potentially change the beam direction. I didn't know before I started working with Oak Ridge, you can actually steer neutrons. And so, and potentially fusion applications could use this. So we've been able to show some simulations, and then we're working on this for the future. So what it's going to have then with the spiking neural networks is we're going to try and figure out how to use this stuff to get more information. And so we're initially working on it with a field programmable gate array, which has the right kind of data stream, as opposed to all the other neural networks. Trying to not fit them in FPGAs is hard for people. And this then will allow you to actually have the information quickly. As we've shown with the smart pixels, you can actually get the information within the 10 nanosecond latency. So that's what we're working on. And so we can make, hopefully, precise position and time resolution. And now everyone's implementing their artificial intelligence on the readout chips. And we're trying to figure out how to do more. Thanks.
Thank you, Alice. Very, very interesting. And that wiring is done in Lawrence?
In Lawrence, yep.
Wow.
All of these. So our technician is having to solder 1,000 cables times 10 pairs, friggin' tiny little wires on connectors.
Wow, and then it needs to be safely transported.
Yeah, that's not a big problem.
Okay.
You know, they're really light and
Wow. Very
pack
cool.
them well. Yeah.
We're ready. Do we have any questions for Alice? We have a couple minutes. Okay, Well, with that, thank you again, Alice. Thank you very much. We'll
Mhm.
turn the proceedings over to Mike Murray. Mike,
Yes, should I share my screen? Yeah, I guess I should.
please.
So, uh, do you see the screen?
Yes.
Yes, we do.
Okay, so rather different. I'll just try to give you a flavor of what we're doing. Title is I'm looking for heavy light with light photons. That's a lot of what the nuclear group is doing at the moment. And I don't know if you've seen the movie Cabrini, but there's many seeds of darkness in it. A lot of time starts going with the nuns going down into the sewers. It's very dark, but there's also many shafts of light. And often we can see a shaft of light by how it reflects, like in dust, or how it reflects off something. But we're going to try to look. Recently, we've been able to see light scattering, not off dust, not off the surface, but of light itself. And now we're trying to see that when light, very intense light, scatters off itself, can we make a new kind of light, maybe a heavier light, a new kind of particle? So that's the essence of what a lot of the effort that we're trying to do in the nuclear group, the CMS nuclear group. So just go to the next slide. Okay. So traditionally, what nuclear physicists do is that they get big things and they smash them together as hard as they can, and like a lot of stuff comes out. And this is a classic example of smashing two heavy things, two lead nuclei together, and we see lots and lots of particles coming out, and we see these sprays of particles, which are very special. They seem to be coming from these heavy quarks called beauty quarks. And then we see a very strange situation where we have electrons and muons coming out, sort of electrons and muons are cousins, but not brother and sister. And this is an indication that what actually happened here was the creation of two top quarks, which decayed into B quarks and neutrinos, and then the B quarks produce electrons and muons. So this is a very nice event, but rather traditional in the sense of what nuclear physics does. So we smash this stuff together, we make this very hot soup of quarks and gluons. This soup is much, say, maybe 1,000,000 times hotter than the sun. And we use how these quarks push through that soup as a probe of the soup. We believe that this soup was something like the matter that was created at the very early universe. And so Professor Takaki and I and Professor Ryan have been doing this for quite some time. And it's told us a lot about the strong nuclear force, about how quarks and gluons behave. And so that's what we're doing at the moment at the Collider in Switzerland. And it's sort of kind of a classic nuclear physics thing. And you could say that it's a complicated mess, but although it's a complicated mess, we do have ways to understand it by looking at these very special combinations of particles that come out. So now I want to look at another thing, which was Daniel did a lot to pioneer this effort, is one criticism of these kind of interactions is it's trying to understand a Swiss watch by smashing the two Swiss watches together and seeing what comes out. So now we've tried a sort of another approach of using these same beams, these same lead beams. We tried another approach. And what you might notice if you've ever seen the movie Top Gun, it's great because there are lots of pictures of sonic booms. Rather than a picture of a sonic boom, you see a shock wave. And this is a shock wave of phonon. So this is a sound shock wave produced because the jets are going so fast. And this shock wave of phonons produces a set of condensation, which looks like a cone. And there's in the movie, I love the movie because there's lots of beautiful pictures of these cones. And now what we try to do at the collider is that you can imagine instead of jets flying together, we have these lead nuclei, and these lead nuclei have a charge of 82. And instead of producing a shock wave of sound, they can produce an electromagnetic shock wave. And instead of a shock front of phonons, of sound particles, they produce a shock wave of photons. And these shock waves are incredibly intense. If you got hit by one, it would be like having like a bullet through your head, much more violent. So it's a tremendously the energy density is an enormous in these things. These have the strongest electromagnetic fields ever created in the universe, and they're really cool for trying to find a new kind of physics. So we have each of the nuclei is producing these shock waves of electromagnetics. Here we see all the jets going in the same direction. But if you can imagine two jets going in opposite directions nearby each other, not hitting each other, but that their shock fronts would hit, then we can see the collisions from the shock fronts. And that's what we're trying to look at now. So here we see a collision where we had two lead nuclei, and the lead nuclei missed each other. They just missed each other. But their shock fronts of photons hit each other. So we essentially had photon-photon collisions. And what we've seen is we've seen lots of different manifestations of these. We've seen photons going to regular light. And here we see two photons going to tau leptons. These are cousins of the electron, but thousands of times heavier than leptons, the electrons. And why we like to look at these taus is because they may be sensitive to some lurking new particle, some lurking heavy photon that might be there. Because the chance of making these taus depends on the number of different ways that they can be made. And so if there's a new particle, there might be more of them than we expect. And their distribution in angle and momentum might be different. And it seems that just with these collisions, we can make very precise measurements of searching for these new particles. So that's like a lot of what our group is doing at the moment. Daniel was very influential in starting this field, but it's coming up. It's doing all sorts of new things now. So this is what we're doing at the Collider at the moment. We're having great fun at the Collider. But the US nuclear community is also building a new accelerator. And I'll talk about that now. So this new accelerator is called the Electron Ion Collider. And there will collide big protons and deuterons and big heavy nuclei with polarized electrons. And so what this will do, it'll go, instead of smashing the Swiss watches together like we were doing in the past, it will actually take like very detailed pictures of intact protons and nucleons. You see not only the quarks and gluons inside them, but the seething mass of gluons and anti-gluon pairs of quarks and anti-quarks. Not just to take a picture, but actually to take a movie of them, how they're correlated in space and time. And so this offers a beautiful way to go to very precise, very detailed images inside of a nucleon at rest, what it actually looks like. And the proton is an amazing thing. It's an incredibly complex object, yet it's been around for 14 billion years. So that's kind of wild. And we would really like to understand how it links together. And then finally, I would like to say that I don't do much of this stuff. Like I work on the budgets and get the people transported and sign papers and stuff like that. And then there's people who actually do the work. So our students, we appreciate your help. So this is one of our pictures of Brittany at CERN. She was great. She got her master's sitting down because she was just going after her master's. She went and had her first baby. And then this is John Paul, who's guinea pig for a new effort at the KU Medical Center using nuclear detectors for radiation therapy. And so thank you very much for what we've done. All you do. Thank you.
Thank you very much. I'm curious if you could tell us a little bit about the collision diagram that you showed.
Oh, yes. For example, this one?
Yes, I didn't really see.
Okay. Yes, you don't see much, that's right. So what is happening at this time is that there is one beam of lead ions coming from the right and another beam of lead atoms coming from the left. And at this particular time when they were crossing, none of the lead ions hit each other. So there was not a direct collision of lead hitting lead. What happened was that the electromagnetic fields of the lead ions made photons. And so each lead ion is bringing with it a sheet of photons. And that sheet of photons from one lead ion collided with the sheet of photons from another lead ion. And so we had a photon-photon collision. And so then this photon-photon, it's like a ball of pure energy. It has 0 quantum numbers, or rather it has the same quantum numbers as the vacuum. And then it could decay. This particular one has decayed into a pair of tau leptons. So the tau lepton is like a heavy electron. Is that helpful?
Yes, so incoming is from the right, the red trace.
No. You imagine the red trace is coming in from the right horizontally, and there's another nucleus coming in from the left horizontally. And what we see is on one side, we see a tau lepton decaying to a muon. That's the red case is the tau decaying into muon. And the green plots are the other tau decaying into an electron and a pair of pions.
Ah, very good. Thank you for the explanation.
I'm sorry, I should have put that on the slide. I
Oh, no
apologize.
worries. Thank you. All right. Well, thank you so much for presenting to us today. And now I'll turn over the MC duties to Daniel.
Thank you, Colleen, and everyone for connecting. Yeah, my name is Daniel Taptakaki. I'm professor in the department and have the pleasure to work with Colleen. And now for the second part, I will introduce Parker Wise is one of the department undergraduate students who has kindly prepared some slides about his work. Parker, the floor is yours. Parker, can you hear me? Okay, I think Parker, if you want, if that's okay with you, we can, while you try to fix the mic problems, we could continue with the program and then we go back to you, if that's fine. So I would suggest now to introduce. Parker, can you repeat again? Okay, so let's go first for Sherry. If that's fine, Parker, while you fix your mic problem. So we have with us Sherry Hamilton. It's also a pleasure to introduce her, and she's our contact in the College of Liberal Arts and Science for KU Endowment. And she also has a few words to say to this meeting. Thank you for connecting, Sherry.
Thank you. Thank you for inviting me here today. It's a pleasure to be with you all. And I am just going to give a brief overview. Sometimes it can kind of, I think, be a bit of a mystery what KU Endowment's doing and how we interface with the university and what our role is. And I'm just going to talk about my team and how we support the College of Liberal Arts and Sciences broadly, but also the physics department. So my name is Sherry Hamilton. I am the Senior Development Director and Team Lead of the College of Liberal Arts and Sciences team. We have, myself included, 4 front-facing fundraisers who work. We live here regionally, but we all have areas throughout the United States that we cover. That we about 1 week of our month is spent on the road. I leave Monday for New York, kind of East Coast. I'll do Connecticut, New Jersey, and New York, and spend time out meeting with alums in those areas. And we cover, there's not quite 60 departments under the umbrella of the college, but then there are in some areas, communications hosts debate, and we have a very, very robust debate team, so they have their own fundraising priorities. We have the Kansas Women's Leadership Institute, which actually is an international organization, also funded through the State Department. So all told, there's the Open Language Resource Center, and many of the studies programs, American Studies, African American Studies. Those areas are all also under our purview, and then university honors. So my team of 4 fundraisers and 2 admins serves roughly 60 departments underneath the college, all who report to our executive dean, Dean Arash Mafi. And then there are 4 associate deans. We report up through with your department, through Dr. Maria Oribe. And so my team, I'll also kind of give a breakdown. So the first level of contact with KU Endowment would be annual giving. Those of us either were probably on this call, we all either work for KU or we were students at KU, or in my case, both. I have 2 degrees, both of which were under the college from KU, and then started with Kansas Public Radio. And I was there, honestly, for almost 2 decades doing development, and then moved over to KU Endowment in 2015, was with the Dole Institute of Politics. One of my degrees is in political science, and then stepped into this role about 1.5 years ago. But I really love being on the academic side. It's amazing. I've always been on the non-academic, KPR and the Dole being like Spencer Museum of Art, lead center of those things that kind of enrich our university, but they're not an actual part of our academic institution in the same way. So we all probably get something in our mailboxes dropped in from KU Endowment in some way, engaging us and asking us to support in a way that is meaningful to us. Usually there's a suggestion there, like maybe the area that you graduated from or that you're most closely associated. That's the first line. And then we have development engagement officers, and they work with university-wide. It's a new program for us. It's only a little over 1 year, but they're working with donors who they don't travel, but they're connecting over LinkedIn and text and email and phone calls from the amounts of about $1,000 on up. And if there's someone who is interested in making a contribution that's above the $25,000 level, then they connect with one of us, which is in the purview of my team. We're meeting primarily, and you might think, gosh, $25,000, but that might be somebody who's giving $5,000 a year for 5 years. That would be considered, a $25,000 gift. We work on with people to find and define something that's meaningful to them in a way that they want to make an impact, whether it's a program, whether it's a student, or faculty support in some way. So that's really for us the lowest, but really our area that we're supposed to really be focusing on is $50,000 and above. That doesn't mean that we don't work with donors in other ways. Not everyone, we don't know until we've made contact with somebody. But for example, the reason when we have it at that number, a scholarship. So when we make a scholarship, most scholarships are endowed, and that means that those scholarships will be there in perpetuity. So a $50,000 investment in a student scholarship will, in perpetuity, if nothing else were ever put in it, the fund will grow, but it's the annual earnings that then provide that support, and it's about $1,100. So we try to keep a student scholarship to where it at least, you know, the minimum that it would produce in a year is about that $1,100, $1,000 mark, with the rising cost of college tuition. That's, you know, kind of the minimum for a scholarship. So anyway, so that's one, you know, that's one area. A huge of importance to the dean is getting more students in scholarship support. Another area of support would be experiential learning, getting graduate students or, you know, undergraduate students out of the classroom to conferences, study abroad opportunities, and not having it just be the kids that can afford it, but that there be some kind of support that that students who want to have these opportunities, that there's a mechanism or a way. Both honors and the college have, and I met Daniel first through the honors program. I know he's involved there. We want to have an emergency fund. It's really important to the dean. We were just talking about the largest class, it's actually the largest class ever, as my understanding, with this freshman class, and next year as many more expected. But we want to make sure that we're retaining them, that we're not bringing them in, having them take on student loans and debts, and have it be that they have a fee or a car that breaks down. We're trying to build in and do fundraising. My team's working on fundraising as one of the dean's priorities of building an emergency fund within the college that they can apply for micro grants through the college. We have it hasn't quite launched yet. We're just, you know, getting gifts in, but that's one of the priorities. And then I would say another main priority for Dean Maffei is faculty support. We want to be able to retain and attract the best and brightest world-class scholars, which, listening to all of you bright minds, there's clearly many of you here. And then lastly, then we have estate giving. And that's if someone wants to include, you know, they might not want to give now, but they're saying, hey, I want to include something for KU or this or project or department or scholarship in my estate plans. And we can also help with that. As far as working with the physics department, we are on target for, you know, I look to see what I don't know if I'm going to say amounts. I would discuss those probably privately with the chair, with Chris. But we've got one, you know, that last quarter of our fiscal year, and we're within $8,000 of where we were last year. So we're looking, you know, we've kept up with that pace. And as you probably have heard, KU Endowment has embarked on a $2.5 billion. I heard someone say here with the cables or the fibers, billion. Yes, it is $1 billion campaign. It's a 10-year campaign. The silent phase started in 2018. We went public in October, and we have until 2028 to hit that goal. The college is the largest academic unit at the University of Kansas, and my team is responsible for a good portion of that. But this does includes our campus here in Lawrence, Salina, Wichita, KU Med, the health systems, athletics, alumni, every facet of KU that you can think of. Any money that's coming in, that will count towards that goal. So that wraps up my my you know, presentation. I didn't have slides or anything, but if anybody has a question for me, I'm happy to take questions as well.
Thank you so much, Sherry. Any questions, comments?
Thank you.
So yeah, thank you so much. So we continue in this conversation, and thank you for connecting, Sherry. So now we have Parker, is an undergraduate student from the department that has a presentation about his work. Parker?
Howdy, can people actually hear me now?
Yeah, very well. Thank you so much for connecting.
Wonderful. Okay. Let me turn my camera on. Howdy. So I'm just gonna speak pretty briefly. I've been asked to kind of come here and talk about my experiences as an undergrad doing research in the department, and just some of the opportunities that I've gotten to do and stuff. So very excited. So I'm going to talk about our summer research program as well a little bit. So just kind of about me a little bit. I work with Professor Mills. I'm looking at a molecular cloud in the center of our galaxy. I use data from the ALMA telescope, pictured right here. Hopefully you can see my cursor. And our goals, so this is the source I'm looking at, and our goals are to be able to get more accurate masses for these sources, as well as getting an idea of the chemical composition of the cloud. Just to kind of show some work that I've done thus far, here's just the spectra. So from this source pictured in that circle, this is a part of the spectra. And as you can see, it's got a lot of lines. So there's a lot going on here. And right now, my work is focused on using models for emission and absorption spectrum and getting that fit to this data so that we can get a good comprehensive view of what molecules are present within this cloud. Some things that I've gotten to do. I'm pictured right here. I was lucky enough to be able to go to the most recent AAS meeting. That was a lot of fun. And I learned a lot. I got to meet some really cool people. And I was even able to, as you can see here, present a poster of mine. Also very informative, being able to talk about my research. And then pictured all the way over here to the right is me at UConn, because Professor Mills has some collaborators up in Connecticut, and I was able to go up there and help work on a project. And they have ice cream, so I took a picture next to their ice cream dog. And I don't have many other pictures from that trip because I suck at taking pictures. But that trip was actually really nice because I was able to go see how research is done on like a different campus. And I worked specifically with a bunch of the grad students. So I got to see and talk and learn from grad students working in a very similar research area that I am. I was also able to do research this past summer here at KU. I worked with Professor Besson, and my goal there was we have this vector network analyzer, which will help like characterize antennas. And my job was to be able to get data from this machine and get it onto another machine. And surprisingly, not that easy, specifically being able to do it quickly and using code to do it. But I was able to get this image over here, pull it off into essentially a .csv file, and then I was able to plot it. At the beginning of that summer, I was also able to do some training. So the training that we would give to RU students, I was able to attend that, and that was very informative, learning specifically about like how to use Bash, things like that. And then I was also able to, and I was given the opportunity to present at the undergrad symposium at the end of the summer. And that was my first time, I think, ever presenting research. So that was very informative. I was kind of nervous about it. But I was very glad I got to do it. And I also don't have pictures from that because, again, I am not very good at taking pictures. But yeah, that is what I wanted to talk about.
Thank you. Thank you, Parker, for your presentation. Are there any comments or questions?
Yeah, hi Parker. This is Mike Rasmussen. I was wondering if you had where is the telescope that you use? Where is that located?
Yeah, so the telescope that my data is from Alma, so that's the Atacama. So I think that's a desert, but it's in Chile. And then it's the large millimeter array, so that's the Alma part of it. That being said, this data that I have, we got it back in like I guess I think it was like 2019, but I could be wrong. It's been a few years since we got the data. Pretty cool.
Okay, any other question? Thank you so much, Parker. It's great that all the work you've been doing and working with, Professor Mills and Besson. That's fantastic. Okay, now we have with us Professor Alison Kirkpatrick. Is a colleague of mine in the faculty for working in astronomy and also associate chair and director of undergraduate studies. Alison, the floor is yours. I think you're muted.
Okay, can you hear me now?
Yes, perfect. Thank you.
Okay, great. Thanks. Yeah, I'm going to talk about undergraduate research in the department. I've got various pictures on this first slide because every summer since I've come, I've organized, I started here in 2018, and every summer since then, I've organized an undergraduate research symposium that's held in August of every year. So perhaps you've seen emails from me about that. And we even had it during COVID. Okay. So just to give you a rundown, our majors our astronomy and physics majors are required to complete one semester of research to earn their degree. And soon with the start of the new school year, this is actually going to be required by the university as well, because every student is going to be required to complete a capstone course. Our research credit will count as their capstone course. Most of our students get involved in research in their sophomore and junior year. Some even start in their freshman year. And our students that get involved early are then able to get enough research experience working with professors in our department that many of them leave us in the summer, and they go get summer research internships at national labs or at other universities. Our undergraduates are really active with conference presentations, both with local conferences and with going to places like the American Physical Society and the American Astronomical Society. And we've had some undergraduates publish. In fact, my first undergraduate paper was published this past week. And just, for those of you who've maybe been out of school for a while, research is now necessary for getting into graduate school. Graduate school is getting highly competitive, and so we need to get our undergraduates to have a good research project to make them competitive applicants. To promote research, we run a summer program called JUST, which is Jayhawk Undergraduate Summer Training. So this is a program that I started back in 2020, And basically, it's to give students a cohesive experience during the summer while they're doing their research. Each week, we organize research talks by faculty, and they'll come in and they'll give talks about their research. We also have professional development workshops, for example, where we talk about coding, learning Python, learning Root, different things like that. But we'll also talk about how to read papers and how to make good presentations. At the end of every summer, we have the undergraduate research symposium. We also organize social programs throughout the summer. And so I just put up here what the schedule of talks was back in 2020, our first year running it. So you could see some of the things that the students learn through this program. Students really enjoy it. Everyone who participates has said that they agree that their physics and astronomy career was helped by their summer research experience and that they really enjoyed being in the department. We do exit surveys at the end of every summer just so we can continually be tweaking and improving our program, but most of them felt like the professional development aspect was really helpful, that we had like dedicated workshops for teaching them how to give talks and teaching them how to write posters and things. Okay, so after 2 years of running just for just our KU students, we were able to levy this into a National Science Foundation Research Experience for Undergraduates program. This is a competitive application process, and through this, we brought in $400,000 to fund a 3-year program where now we bring in outside students to our department. And again, we run the same programming we've been doing with professional development and a symposium. And these external students have a fully funded summer experience. The NSF covers like their dorms, it covers their travel. We pay for them to go to a conference and we give them a stipend. It's a very popular program. This year alone, we had 150 applicants, and unfortunately, we can only take 10 people. So REU programs are really competitive, and we offer projects in all of our departments' areas of expertise. So astronomy, high energy physics, condensed matter, and physics education research. Just to give you an idea of where people come from, in 2023, this is where all of the people who participated in our program it came from. We had someone as far away as Puerto Rico. All right, so finally, the reason I was asked to talk about undergraduate research is this year we have a Launch KU campaign running. So this is a crowdfunding campaign. It runs for another, I think, 17 days. And the purpose of this is that, so our NSF program pays stipends to external applicants. We cannot fund our own students off of it. And it is getting harder and harder out there to pay undergraduate researchers because budgets are tight right now. And so we wanted to create a way to pay KU students, because I get asked every year by KU students, can I apply for our REU? And I have to tell them, no, they can't. So we wanted to come up with a way that we could pay KU students. So if a professor doesn't have money, but they still want to take on a student, they can still advertise a project. And so that's where our crowdfunding campaign came in. So the idea is that we want to try to create 2 summer fellowships. And the Physics and Astronomy Alumni Board, you all have been so wonderful, and you've helped us get over halfway to our goal. You all were very generous in doing a matching gift, and so we already have 1 fellowship funded, and so we're trying to get to 10K to fund the second fellowship as well. And I will do a better job, I guess, of advertising our undergraduate symposium. Hopefully you all have heard about it, But if you haven't, I will reach out to the Physics and Alumni Board directly, because we want to make this an event that anyone associated with the department or any donor can come to. We always have a reception afterwards with food as well. And it's also always online, because a lot of our students, it's very cute, their parents want to watch them. And so it's also always streamed so that people all over the US can tune in and watch undergrads talk about what they learned this summer. Yeah, okay, so I'll take questions if there are any.
Thank you so much, Alison, for all this fantastic work and effort. Any questions? Comments? Colleen, do you have any questions or comments?
No questions,
Okay.
but thanks for the thanks. It was a privilege to help your campaign, Allison, and I'm glad it went so well so far.
So thank you so much, Alison. Okay, so now I have promised that I will also show just a couple of things that from the, we also have the in the department, the graduate program, and Professor Casey Cohn, who is the director of graduate studies at the moment, and I made a survey last year, and we had some meetings to identify some needs for targeting the international community in the department, for undergraduates, but also graduate students. But in the case of international students, we have identified some needs, and one of them is to recognize the importance that they bring, the values and different perspective and experience and the skill that they bring to enrich the intellectual and cultural environment of the whole department. And also recognize that, there are some financial burdens that are there, and they represent some kind of obstacle for recruiting some global talents. And this has been recognized for many associations like the American Physical Society and others for supporting the PhD graduate program. Those include things like application fees, the cost, the relocation costs, the opportunities that they have for experiential learning, which is, there are not all the opportunities that domestic students find, and recognizing this and trying to find ways to support them, not just financially, but also in administrative ways is very important. And I think the department is working very hard on this. One of the things that also was identified is the fact that sometimes, not just in our department, but nationwide, there is some studies on several universities about the need of guarantee faculty independent transition funding. That's how they call it, for graduate students to feel free that they can switch between research groups. And this has been identifying different venues recently in the last couple of years as something that is needed for promoting a more welcoming and more creative research environment. And because of this reason, we have also a new, not a campaign like the one that Professor Kirkpatrick has mentioned, but more like a new fund that has been opened for supporting in general international graduate students. And I just wanted to mention this to everyone. And the second point I wanted to mention is that we also have a new initiative that is joining some of this. So we're organizing our own network events. Okay, KU Alumni Association has been organizing this for a few years. And in the department, we want to partner this together with the ongoing national conference in physics and astronomy. We are going to do a first one in Phoenix, Arizona, that is usually done as a cocktail evening where anyone from the interested can join in an informal setting to discuss the different professional journeys and to learn from students and faculty that attend those national conferences. We decided this Phoenix because this is the one where we have the SACNES conference, is the largest STEAM fields conference for advancing Chicano, Hispanic, and Native Americans, and many people, students and faculty from the department participate. That's going to be there. But we expect similar things will happen for other events like the astronomy conference and the physics conference, and this will be one of the first tests that we're going to do, and invitations will be circulated later in the next few months. But I wanted to have a head-ups for this event. So these are the two things that I wanted to mention. If there are any comments or questions. Okay. Colleen, do you have any comments? Or?
No comments. Daniel, if we're ready to close, perhaps you'll let me share my screen. I want to show the contact information.
Excellent.
Oh,
I can see it. Yeah. Mhm.
okay, very good. Yes, so I just wanted to provide contact information if anyone wants to be a part of the PAAB or has any other reason for wanting to contact the department. Please don't hesitate to start with us.
Your screen just went blank, Colleen.
Oh, thank you.
Okay. Are there any other comments or questions? Okay, Colleen, I think the floor is yours. If you want to say some last remarks. Colleen, can you hear me?
Yes, I'm sorry, please say again.
If you want to say some last remarks before closing.
No, I just want to thank everyone who joined the call today. Daniel, I don't know about your feelings. I think I'm very proud of our department and very proud of its alums and faculty and students. And it's great to have events such as these. And I hope we can make a tradition of it and have another Zoom event in the future.
Yes, and thank you for all the work that you've been doing and all the alumni boards. So we are very happy to have a very, active and engaged as we have seen through all these years. And thank you for all your work. I think I can say this on behalf of the department and Chris Fisher here at Department Fisher.
Yeah, thank you very much, Colleen. We all really appreciate it. And thank you, Daniel, for all of your work.
Yes, thanks, Daniel.
Okay. Well, thank you, everyone. So speak to you soon. Bye-bye.
Thank you.
Thank you,
Okay,
Colleen.
thanks,
Great job,
thanks,
Chris and
Judy.
Daniel.
Bye-bye now. Thanks, Judy. Bye.